Hi, and welcome to this short concept bite introducing the concept of Gibbs free energy, explaining how it derives from the second law of thermodynamics and why it is so important. So far, we've seen independently the concepts of both enthalpy and entropy, and it is the Gibbs free energy which connects these two important concepts. You will recall that one of our possible statements of the second law of thermodynamics was the entropy of a universe increases during any spontaneous change. Spontaneity is important. Any reaction which is spontaneous has the ability to do work. We can make any reaction which is not spontaneous happen by doing work. But how can we work out how much work a system can do? Well, that is what the Gibbs free energy is telling us. Firstly, it is important to remember that there is an entropy change in both the system and surroundings, and it is unlikely that these will be equal and opposite. If we are at constant pressure, then the heat transferred to the surroundings is delta H. For processes that are fully reversible, the net change in entropy of the universe is zero. However, most processes are irreversible, and so, to follow the second law, the total change of entropy has to be greater than zero. J.W. Gibbs' contribution to thermodynamics was to combine the equations for entropy of the system and surroundings. He said that if we are at constant pressure and temperature, then we can substitute delta H for Q rev, and the total change in the entropy of the universe can now be defined with only variables of the system. Now we define the Gibbs free energy as minus T delta S total, which gives us one of the most important equations in chemistry. The Gibbs equation. Delta G in this equation is called the driving force of the reaction. Because of the relationship to the entropy of the universe, when delta G is negative, the reaction is spontaneous because the total entropy of the universe is increasing. Delta G is telling us the maximum amount of non-expansion work that can be extracted from a chemical process. The system can do work. This might be raising a weight in a gravitational field, or powering an iPhone, or powering biological life. Since enthalpy, entropy and temperature are all state functions, so is the Gibbs free energy. This means that it doesn't matter the route by which a state function is reached, we can use the same products minus reactants approach we used elsewhere. There is an equivalent to Gibbs free energy if our system is at constant volume and temperature and does no expansion work. This is called the Helmholtz free energy and it has the symbol A because H was already taken. This isn't used a lot in chemistry as most of our reactions are carried out on an open bench at atmospheric pressure, but I've included it for completeness. The Gibbs free energy is one of the most important concepts in thermodynamics. It is what tells us if a chemical reaction will occur at particular temperatures, and it tells us how much work we can get from the system. I hope that this video has helped explain where this equation comes from and how it relates to the second law of thermodynamics. If you have any questions, please do not hesitate to ask.